Welcome to Talkcast and to part 3, or is it 4, on chapter 11 of The Fabric of Reality, Time, the first quantum concept. Now, last time I talked about time, I spoke to researcher Sam Kuipers, colleague of David Deutsch, about much of this material that we're going to go over again today. But we're going to be able to refine some of the content in this chapter in light of recent scientific discoveries, as well as what we've already talked about on this issue of time. Time's a slippery concept. When we think about what the flow of time is, the grammar that we use seems to conjure this fluid of a kind, passing either through us or we through it. There is a motion associated with time, it seems, in our minds. But this just isn't true. What's really going on is that there is difference moment to moment, but no flow. How can we make sense of this? And this is what we're trying to do. We're trying to come to some common understanding about what this entity, a part of physics, attempting to be described by two quite different theories. On the one hand, general relativity, and on the other, quantum theory. Quantum theory describes a multiverse, so what is the place of time in this multiverse? How can it be understood? This is really what we're focusing on in this episode today. So therefore, without further ado, let's go straight to the book and straight into the readings. David Deutsch says, quote, "If the multiverse were literally a collection of space-times, the quantum concept of time would be the same as the classical one. As figure 11.6 shows, time would be a sequence of moments. The only difference would be that at a particular moment in the multiverse, many universes would exist instead of one. Physical reality at a particular moment would be, in effect, a super snapshot consisting of snapshots of many different versions of the whole of space." Pause there, my reflection. So this idea that the multiverse is simply a collection or an ensemble of many universes, many classical space-times, all there existing in parallel in a sense, only rarely interacting, but basically each of them a cosmological physical reality in and of itself, is misleading. Because universe is not properly defined easily within the Everettian multiverse explanation of what's going on with quantum theory. The concept of a universe emerges out of a more fundamental understanding of what the multiverse is. The multiverse is physical reality. What a universe is a way of talking about a common history of objects within a slice, if you like, of that multiverse. So we can't really talk about the multiverse as just being a set of parallel universes. It's not that. It's much more. It includes things like fungible objects and entanglement. Let's keep going. Because of quantum interference, each snapshot would no longer be determined entirely by previous snapshots of the same spacetime, though it would approximately, because classical physics is often a good approximation to quantum physics. But the super snapshots beginning with a particular moment would be entirely exactly determined by the previous super snapshots. This complete determinism would not give rise to complete predictability, even in principle, because making a prediction would require a knowledge of what had happened in all the universes, and each copy of us can directly perceive only one universe. Nevertheless, as far as the concept of time is concerned, the picture would be just like a space-time with a sequence of moments related by deterministic laws, only with more happening at each moment, but most of it hidden from any one copy of any observer." End quote. And let me expand on this idea that something can be both determined and yet unpredictable. Determined to be unpredictable. There are two examples that we might like to use here. A single photon of light heading towards a half-silvered mirror. Now, it's completely determined by the law of physics that either it's going to pass through that mirror, be transmitted, or it's going to bounce off, it's going to be reflected. One of those two things is going to happen, but you cannot predict which ahead of time. It's unpredictable. It is determined to be unpredictable. It is determined by the quantum laws of physics as to what will happen, but you can't predict it. You are subjectively in one universe, and you will only know which universe, the transmission universe or the reflection universe, once you've performed the experiment, once you've seen what it actually does. Does it go through, or does it bounce off? That's on the one hand. And on the other hand, we have this thing called knowledge creation. The future course of the universe depends upon what choices people are yet to make, what problems they will encounter, what solutions they will conjecture, and that makes the future inherently unpredictable as well. But never mind all that, we're still talking quantum theory, although these things are related. These things are related. Quantum theory allows for this open-ended future, even if the past appears to be fixed. Let's keep going. David writes, quote, "However, that is not quite how the multiverse is. A workable quantum theory of time, which would also be the quantum theory of gravity, has been a tantalizing and unattained goal of theoretical physics for some decades now. But we know enough about it to know that though the laws of quantum physics are perfectly deterministic at the multiverse level, they do not partition the multiverse in the manner of figure 11.6 into separate spacetimes or into super snapshots of each other, which entirely determines the others. So we know that the classical concept of time as a sequence of moments cannot be true, though it does provide a good approximation in many circumstances, that is, in many regions of the multiverse." End quote. So it's a good approximation, this idea of time as a sequence of moments. But there are a lot of good approximations in physics, but that doesn't make them true. Newton's force law of gravity, the inverse square law, famously not true, but hey, very useful approximation if you just want to make predictions, if you want a basic first pass understanding of this concept of what gravity is. There's certainly an influence between these masses separated by some distance, but it's not a force. It's not mediated by bosons. That much we know because we have this other theory called general relativity, which seems to rule that out. We need to reconcile the two. We're yet to get there yet. We're yet to find a quantum theory of gravity, which may or may not involve bosons. Who knows? Now, there is this interesting phenomena known well in everything from special relativity through to general relativity, that there is no one single now. That now is unique to a person, to a particular place in space-time. Now, for me, is meaningless for someone on a planet orbiting a star in the Andromeda Galaxy. There's no now that is simultaneous between those two things. This is the relativity of simultaneity. Now, it only gets worse when we get into quantum theory and we're talking about other universes. And in these other universes, to talk about now as being the same time as some other now in those universes would be to presume that there is a clock outside of the multiverse ticking away, keeping track of when now actually is. But there is no such clock. There is no time outside of the multiverse. And so David goes on to say, quote, "To elucidate the quantum concept of time, let us imagine that we have sliced the multiverse into a heap of individual snapshots, just as we did with space-time." And he then goes on with the argument, and I point you to page 278, but I'm going to skip the argument and just give you the conclusion, because the conclusion is the most important part for everyone to remember. And that conclusion is, other times are just special cases of other universes. I'll say that again. Other times are just special cases of other universes. Everything that's happening now to you as a matter of consciousness, that's a universe that you're in. But you've just left a different universe, a way of slicing up this multiverse, moment to moment in your history, if you like. And in the future, there will be more moments, other universes that you are transitioning between, going from universe to universe with a common history. A universe is just a particular way that might be convenient of slicing into the multiverse. You've got this ensemble of universe, this class of universes, all of which obey the same physical laws. But if you slice it up horizontally or vertically or whatever analogy you might like, you get a universe. So you are in a universe right now, a part of the multiverse. And in the future, you will be in a different part of the multiverse, a different universe. Other times are just special cases of other universes. So David goes on to explain some of the history as to why we now think of other times as special cases of other universes. And he writes, quote, "This understanding first emerged from early research on quantum gravity in the 1960s, in particular from the work of Bryce DeWitt. But to the best of my knowledge, it was not stated in a general way until 1983 by Don Page and William Wouters. The snapshots which we call other times in our universe are distinguished from other universes only from our perspective, and only in that they are especially closely related to ours by the laws of physics. They are therefore the ones whose existence our own snapshot holds the most evidence For that reason, we discovered them thousands of years before we discovered the rest of the multiverse, which impinges on us very weakly by comparison, through interference effects. We evolved special language constructs, past and future forms of verbs, for talking about them. We also evolved other constructs, such as if-then statements, and conditional and subjunctive forms of verbs for talking about other types of snapshot without even knowing that they exist. We have traditionally placed these two types of snapshots, other times and other universes, in entirely different conceptual categories. Now we see that this distinction is unnecessary." End quote. Isn't that marvelous? Now remember, one way of looking at the multiverse is as that physical reality where what the laws of physics permit to happen will happen somewhere. Now, it won't happen with equal measure, that's a technical term, in equal proportion, but if the laws of physics permit it, it's possible. And if it's possible, it happens somewhere in the range of all things that are physically able to happen. And that's the multiverse. But don't be misled. It's not like in some universes, all the cures to all the diseases happen as a matter of causality. Although that is true, that's almost like a Harry Potter universe. What we want is to construct the knowledge so that that knowledge of how to cure disease or whatever it happens to be is able to be instantiated in a physical substrate in a resilient way so that it tends to cause itself to continue to get copied over time, which we call knowledge. It's not merely an ever smaller proportion of universes that appear to have created knowledge. And this is a little bit esoteric, but see my series on the multiverse for more about that. Whatever the case, we can also see here the nascent beginnings of constructor theory, this idea of certain kinds of verbs that talk about alternatives to what happened in our universe as being possibilities, things that happen elsewhere in the multiverse, as well as those things that did actually happen in our universe, but then, okay, sometime in the past, they really did happen, and will happen in the future. There's a prediction. But in any case, this idea that there are versions of you in the past, versions of you in the future, and versions of you essentially parallel, let's say, means that, well, the question of what you are in the multiverse is an interesting one. Now, I've made videos about this before. Here's one. Look up the Nexus if you happen to be listening. Otherwise, let's go to the book and see what David has to say about this. Quote, "If, aside from variants of me in other universes, there are also multiple identical copies of me, which one am I? I am, of course, all of them. Each of them has just asked that question, which one am I? And any true way of answering that question must give each of them the same answer. To assume that it is physically meaningful to ask which of the identical copies is me is to assume that there is some frame of reference outside the multiverse relative to which the answer could be given. I am the third one from the left," and so on. End quote. So we have to be careful here. Remember that David Deutsch refines the language of identical that he's using here in The Fabric of Reality to fungible when it comes to chapter 10 of The Beginning of Infinity. There we talk about more identical than identical. So right now, as a matter of fact, there are versions of you that are exactly like you in this universe, but they exist in other universes. They are you, and you are them, and that is what it's like to be an entity spread across the multiverse. Now, there also are copies of you that right now go off and hitherto have been doing exactly the same thing, but now go and do something else. So instead of continuing to listen to me, they walk off to go and have a cup of tea or something like that. And that, although it's a copy of you that was hitherto identical to you, once it ceases to be identical and therefore differentiates from you, is no longer in any real sense you. It's a version of you, but you are now having different conscious experiences. One of you is having the experience of brewing up a hot cup of tea, and the other is continuing to listen to my voice, or watching me on the screen, as the case may be. So it is the fungible copies of you for which it is not meaningful to ask, which of them is you? They're all you. You are an uncountably infinite number of fungible instances of yourself spread across the multiverse, even if you only experience the same universe, because that universe that you're experiencing, it has also all of its objects in fungible instances right now that at every single moment are also differentiating into different measures, different parts of the multiverse. Skipping a little more, David goes on to say, quote, "Quantum theory does not in general determine what will happen in a particular snapshot, as space-time physics does. Instead, it determines what proportion of all snapshots in the multiverse will have a given property. For this reason, we inhabitants of the multiverse can sometimes only make probabilistic predictions of our own experience, even though what will happen in the multiverse is completely determined. A typical prediction of quantum theory might be that if in a certain number of snapshots a coin has been set spinning in a certain manner and clocks show a certain reading, then there will also exist half that number of universes in which the clocks show a higher reading and the coin has fallen with heads upwards, and another half in which the clocks show that the higher reading and in the coin has fallen with tails upwards." End quote. Now, of course, David would be the first to concede that in his more recent work on probability and how it does not govern, it is not a fundamental feature of physical reality. It is a, as we say, with Newtonian gravity or whatever else, it's a good approximation in certain circumstances to rely upon the heuristic, which we might call probability. However, it doesn't really govern what's going on at the level of fundamental physics. In particular, coins. Coins obey the quantum laws of physics. And there is no such thing as a perfectly ideal coin. So when you flip a coin, it's never true that it's perfectly 50-50. I mean, just flip a coin yourself and you will see deviations from this so-called 50-50. Now, if you say, well, probability is that it converges on 50-50, well, how do you know that it should converge on 50-50 given a real coin, once again, obeys the laws of physics? Perhaps it's slightly weighted more towards heads than tails. You can't rule these things out. We don't know. But what we do know is that to some approximation, some of the time, we can use things like probability, the probability calculus, in order to give us something like the approximate known probability for an object like a dice or a coin, where we know what the possible outcomes are going to be, more or less, ignoring the random things that can and do happen in the multiverse. For example, when you flip the coin and it turns into a butterfly, that's physically possible and does happen in some ridiculously small measure of universes. It happens, and so it violates this strict 50-50 heads versus tails probability. But to a good first approximation, we can talk about it's 50% heads, 50% tails. Those are the options. We ignore it landing on its edge. We ignore it vaporizing into mist, that kind of thing. But those things, if you're going to be strict, and refer, please, to this particular lecture, it's a wonderful one, so underrated, all about the place of probability in physics. Namely, we can eviscerate it from physics. It's not part of fundamental physics. The laws of quantum theory determine what happens in physical reality, not the probability calculus, which was basically invented for gambling. Skipping some more substantial parts of the text and picking it up where David says, quote, "The determinism of quantum theory, just like that of classical physics, works both forwards and backwards in time. From the state of the combined collection of heads and tails, snapshots, at the later time, in figure 11.7, the spinning state of a coin at an earlier time is completely determined, and vice versa. Nevertheless, from the point of view of any observer, information is lost in the coin-tossing process. For whereas the initial spinning state of the coin may be experienced by an observer, the final combined heads and tails state does not correspond to any possible experience of the observer." Pausing there in my reflection. So in the multiverse, both outcomes happen when a coin is tossed. It lands both heads and tails. Not in equal measure necessarily, it depends upon how ideal the coin happens to be. But you end up with this superposition of states. But no single observer ever observes that outcome, both heads and tails. They observe one or the other. They're not causing one or the other. It's just that they happen to experience being in a universe where it definitely lands heads, or XOR, okay, exclusive OR, lands tails. So, just to repeat, the final combined heads and tails state does not correspond to any possible experience of the observer. Therefore, an observer at the earlier time may observe the coin and predict its future state and the consequent subjective probabilities, but none of the later copies of the observer can possibly observe the information necessary to retrodict the spinning state. For that information is by then distributed across two different types of universe, and that makes retrodiction from the final state of the coin impossible. For example, if all we know is that the coin is showing heads, the state a few seconds earlier might have been the state I called spinning, or the coin might have been spinning in the opposite direction, or it might have been showing heads all the time. There is no possibility of retrodiction here, even probabilistic retrodiction. The earlier state of the coin is simply not determined by the later state of the head snapshots, but only by the joint state of the heads and the tails snapshot. End quote. So that's beautiful. So if you're in a universe, you don't have access to all the information that is required in order to retrodict your way back to what caused the outcome that you're seeing. You have to speak in terms of those other universes, the unobserved things that you don't have access to, but which form a crucial part of the good, hard-to-vary explanation. It's exactly analogous to Chapter 2, Shadows, where we're invoking the existence of photons we do not observe to explain the path taken by the one we do observe. Skipping some more, David goes on to say, quote, "In space-time physics, any snapshot is determined by any other. As I have said, in the multiverse, that is in general not so. Typically, the state of one group of identical snapshots, such as the ones in which the coin is spinning, determines the state of an equal number of differing snapshots, such as the heads and tails ones. Because of the time reversibility property of the laws of quantum physics, the overall multi-valued state of the latter group also determines the state of the former. However, in some regions of the multiverse and in some places in space, the snapshots of some physical objects do fall for a period into chains, each of whose members determines all the others to a good approximation. Successive snapshots of the solar system would be the standard example. In such regions, classical physical laws are a good approximation to the quantum ones. In those regions and places, the multiverse does indeed look as in Figure 11.6, a collection of spacetimes, and at that level of approximation, the quantum concept of time reduces to the classical one. One can distinguish approximately between different times and different universes, and time is approximately a sequence of moments. But that approximation always breaks down if one examines the snapshots in more detail, or looks far forwards or backwards in time, or far afield in the multiverse. All experimental results currently available to us are compatible with the approximation that time is a sequence of moments. We do not expect that approximation to break down in any foreseeable terrestrial experiment, but theory tells us that it must break down badly in certain types of physical process. The first is the beginning of the universe, the Big Bang. According to classical physics, time began at a moment when space was infinitely dense and occupied only a single point, and before that there were no moments. According to quantum physics, as best we can tell, the snapshots very near the Big Bang are not in any particular order. The sequential property of time does not begin at the Big Bang, but at some later time. In the nature of things, it does not make sense to ask how much later. But we can say that the earliest moments, which are, to a good approximation, sequential, occur roughly when classical physics would extrapolate that the Big Bang had happened 10 to the power of minus 43 seconds, the Planck time, earlier. A second and similar sort of breakdown of the sequence of time is thought to occur in the interiors of black holes, and at the final recollapse of the universe, the Big Crunch, if there is one. In both cases, matter is compressed to infinite density according to classical physics, just as the Big Bang and the resulting gravitational forces tear the fabric of space-time apart. End quote. So many people will be able to guess the note that I'm going to make right here. This book was published in 1997, The Fabric of Reality. And in 1998, two research teams, both researching supernovae, discovered, to our continued surprise, that the universe is not slowing down at all in its expansion. There is not going to be a big crunch. There's not going to be a end to the expansion and then a collapse under gravity of all the matter in the universe back to a new Big Bang of some kind. No, the universe is going to continue to expand, but not only that, it is accelerating. Right now, its expansion. The expansion is getting faster and faster and faster. Something is driving the universe to accelerate the flinging apart of galaxies as the space between them grows ever larger at an increasing rate, due to an energy source that we have no idea how it works, what it is, what the nature of this expansion is or anything, and so we call it dark energy. It's the dark energy problem that's not a solution. And so we can rule out the Big Crunch now, given observation. But what can we rule in? We don't know. All we see is, according to our best measurements of distant supernovae in very distant galaxies is that the universe is flying apart faster and faster and faster. Something is driving this accelerating expansion. So that changed just 1 year after this was written, and so it has a few consequences for, the chapters that are coming. But here we go. Here's one correction to that. And you can go to my questions for David, where I've asked him about this particular thing, by the way. Let's keep going with the reading. David says, quote, "By the way, if you have ever wondered what happened before the Big Bang, or what would happen after the Big Crunch, or after the universe has expanded itself such that all subatomic particles are themselves ripped apart, you can stop wondering now. Why is it hard to accept that there are no moments before the Big Bang or after the Big Crunch, so that nothing happens or exists there? Because it is hard to imagine time coming to a halt or starting up. But then, time does not have to come to a halt or start up, for it does not move at all. The multiverse does not come into existence or cease to exist. Those terms presuppose the flow of time. It is only imagining the flow of time that makes us wonder what happened before or after the whole of physical reality." End quote. Yes, as any science, especially physics, astronomy popularizer knows, one of the first questions one tends to get asked is, once one's delivered a lecture or a presentation or something that touches on any of these questions that at all circulate the Big Bang, is what happened before the creation of the universe? What happened before time? What was time before time like? And of course, the question makes no sense. People want to know why the universe, of course. So why is there existence? And we don't have an answer to that. We just keep pushing the answer back further and further. But perhaps construct a theory, this theory that is going to distinguish for us, we hope, what it means for something to be physically possible versus something impossible, and to have a sharp demarcation criterion between those two things under certain scientific theories and physical laws. That might just give us a clue about why the universe, why this multiverse, why this set of physical laws. But we don't have that yet. But there's no point asking what was happening before the creation of time, because that presupposes a time before time, a time flowing outside of the multiverse. David goes on to say, quote, "Thirdly, it is thought that on submicroscopic scale, quantum effects again warp and tear the fabric of space-time, and that closed loops of time, in effect tiny time machines, exist on that scale. As we shall see in the next chapter, this sort of breakdown of the sequence of time is also physically possible on a large scale, and it is an open question whether it occurs near such objects as rotating black holes. Thus, although we cannot yet detect any of these effects, our best theories already tell us that space-time physics is never an exact description of reality. However good an approximation it is, time in reality must be fundamentally different from the linear sequence which common sense supposes. Nevertheless, everything in the multiverse is determined just as rigidly as in classical space-time. Remove one snapshot and the remaining ones determine it exactly. Remove most snapshots and the few remaining ones may still determine everything that was removed, just as they do in space-time. The difference is only that, unlike space-time, the multiverse does not consist of the mutually determining layers I have called super snapshots, which could serve as moments of the multiverse. It is a complex, multi-dimensional jigsaw puzzle. It is this jigsaw puzzle multiverse which neither consists of a sequence of moments nor permits the flow of time. The common sense concept of cause and effect makes perfect sense. The problem that we have found with causation in space-time was that it is a property of variance of the causes and effects, as well as of the causes and effects themselves. Since those variants existed only in our imagination and not in space-time, we ran up against the physical meaninglessness of drawing substantive conclusions from the imagined properties of non-existent, counterfactual physical processes. But in the multiverse, variants do exist in different proportions, and they obey definite deterministic laws. Given those laws, it is an objective fact which events make a difference to the occurrence of which other events." End quote. Beautiful. And there we have it again, invoking a sort of nascent constructor theoretic way of understanding what's going on here. The counterfactual parts of reality really do exist. They're there in the multiverse, but not in equal proportion, in different proportions, and obeying definite deterministic laws. So what you could have done, you did really do in some other part of the multiverse, as long as it obeys the laws of physics. skipping a little and picking it up where David touches on the very interesting philosophical distinction between the possible and the actual. And of course, in the multiverse, all possibles are actuals somewhere, with a proviso. Again, not with equal measure. We need to actively create knowledge to make the possible actual in large proportion. However, as David says here in this chapter, quote, "The conversion relative to any observer of possibilities into actualities, of an open future into a fixed past, also makes sense in this framework. Consider the coin tossing example again. Before the coin toss, the future is open from the point of view of an observer, in the sense that it is still possible that either outcome, heads or tails, will be observed by that observer. From that observer's point of view, both outcomes are possibilities, even though objectively they are both actualities. After the coin is settled, the copies of the observer have differentiated into two groups. Each observer has observed and remembers only one outcome of the coin toss. Thus, the outcome, once it is in the past of any observer, has become single-valued and actual for every copy of the observer, even though, from the multiverse point of view, it is just as two-valued as ever." Pausing there, my reflection, and I'm sure David will not mind me using his yet-to-be-published book as of 1997 in his own future, possible future, The Beginning of Infinity, where he does talk about, and in fact, even here in The Fabric of Reality, he talks about the things unexpected that are consistent with the laws of physics that actually do occur in rather small measure at the multiverse. So we're simplifying things here to say that there's only a two-valued option here for the tossing of the coin. Tossing a coin in the overwhelming majority of the multiverse partitions itself into approximately 50-50, okay, heads and tails. But there is a very, very small number of places where it lands on its edge, where it vaporizes into mist, where it turns into something else without violating conservation of energy laws, that kind of thing. So these things do happen in the multiverse, these chains of highly unlikely coincidences, which do alter this strict 50-50, but this is a nice approximation. As I like to say, probability is to quantum theory as Newton's inverse square law is to gravitation. Let's keep going. David says, quote, "Let me sum up the events of the quantum concept of time. Time is not a sequence of moments, nor does it flow. Yet our intuitions about the properties of time are broadly true. Certain events are indeed causes and effects of one another. Relative to an observer, the future is indeed open and the past fixed, and the possibilities do indeed become actualities. The reason why our traditional theories of time are nonsense is they try to express these true intuitions within the framework of a false classical physics. In quantum physics, they make sense, because time was a quantum concept all along. We exist in multiple versions, in universes called moments. Each version of us is not directly aware of the others, but has evidence of their existence because physical laws link the contents of different universes. It is tempting to suppose that the moment of which we are aware is the only real one, or is at least a little more real than the others. But that is just solipsism. All moments are physically real. The whole of the multiverse is physically real. Nothing else is." End quote. What a wonderful way to end the chapter. But what makes this present moment special? Well, our consciousness does. And we are conscious at a moment. But it's not to say that other instances of us are not conscious. They are. This gets to the heart of the mystery about consciousness. We don't know what it is. We don't have a good explanation. One day we will, and it will resolve these seeming paradoxes. Why are you conscious of this moment and not other moments? Well, why are you conscious of this particular space and not other spaces? Well, because you're not in that other space. You're not over there. You're here. And not only are you here, you're here now. And that's always true. Let's have a look, by the way, at the terminology at the end of this chapter, because I think it's very instructive. And it leads into, well, some of my favourite topics, of course. So he begins with, quote, "The flow of time. The supposed motion of the present moment in the future direction, or the supposed motion of our consciousness from one moment to another. This is nonsense. We exist at moments. We do exist at moments, but we're not flowing, moving through or anything like that." Next, space-time. Space and time considered together as a static four-dimensional entity. space-time physics, theories such as relativity, in which reality is considered to be a space-time. Because reality is a multiverse, such theories can at best be approximations. Free will, the capacity to affect future events in any one of several possible ways, and to choose which shall occur. I might add my own little flourish on this. It's also the capacity to create things in the world from which you can then choose. So, yes, free will is about this capacity to choose, but it must be intimately tied as well to something that other animals simply cannot do, which is to create a new option. There's a great debate going on in Australia right now. Should we have nuclear energy? Now, whether the answer is yes, we should or we shouldn't, that doesn't worry me right now. I think we should. But the interesting thing is, that question could not have been asked in 1850 because no one knew about nuclear physics. The fact that we created the domain of knowledge known as nuclear physics means that we now have the option on the table that we can freely choose. And so free will is tied intimately to this concept of knowledge creation. David goes on to outline some more terminology. Counterfactual conditional. A conditional statement whose premise is false, such as, if Faraday had died in 1830, then X would have happened. Okay, so this is laying the foundations, if you like, for constructor theory. Snapshot. A universe at a particular time. And the summary here is just wonderful because it's so short. The summary of the chapter is, time does not flow. Other times are just special cases of other universes. So that's a wonderful way to leave this chapter, and what a marvellous chapter it has been. An exploration of this concept of time, challenging our intuitions in terms of common sense, and as well as understanding that that other theory, general relativity, which is about space-time, cannot be the final word about what time is. It challenges our intuitions enough. In fact, in some sense, many people struggle even more with relativity. This idea that you cannot have simultaneous events, this idea that time can dilate or that lengths can contract and all that kind of thing. It can be very interesting to learn, but very difficult if you don't have the background to appreciate what is genuinely going on. What comes next is time travel, and I can't wait to get to time travel to talk about all the ways in which we might be able to go into the past. We're always going into the future, aren't we? Well, at least moment to moment, things are changing. Change is occurring, as I spoke to Sam Kuipers about. And that's what we know, that time is, in a very real sense, change. Would it be possible to change in such a way that we can experience our own past? Not merely look like we look at a movie or see pictures, because we can experience our past in a certain way, going through the photographs on our phone or in the photo album or something like that, but actually go there, to actually go to the past. Is it physically possible? We'll talk about that next time. If you'd like to support me, please go to www.bretthall.org right here and click on the donate buttons. Go to Patreon and sign up as a subscriber. I hope to be doing a few more Ask Me Anything episodes in the near future, and Patreons always get priority with those. Until then, bye-bye.